in many applications, it is important to be able to decompose a given vector, say u, into the sum of two vectors, one that is parallel to another vector and one that is perpendicular or orthogonal to that other vector. So that sounds, a little convoluted when I say it, but let's start with the picture. That will really help. So let's say I have a vector u, and again, it can be in any dimension, 2 or 3 or even higher, right? So let's say this is the vector u. And just for convenience, what I'm going to do is I'm going to draw the vector v like this. So here's the other vector v, right? So our first assumption is that u and v are concurrent non-zero vectors. Now remember, concurrent is saying that they have the same initial point, and then obviously non-zero is that they both have some magnitude and some direction. So what I would like to be able to do is to express the vector u as the sum of two other vectors, one that is parallel to v, so it can either be going this way or back this way. In this case, it's going to move in this direction. And then another vector that is perpendicular or orthogonal to v. So let me sketch what the two vectors are going to look like. So the first, in fact, let me do this first. I am going to draw basically, let me do this in blue. Right, so I'm going to create like a little right triangle there. And then the vector that will be parallel to v will be this vector. So it will look like that. And I'm going to call it w1, right? So, and then the other vector now that will be perpendicular to v will be that one that I actually have there in blue. So it'll be this vector. And it will go this way. So that will be, and I'll call that one w2. So just by looking at the geometry of this, I can see that the vector u, which goes from this initial point to this terminal point, can be expressed as first going in the direction of w1 and then plus going in the direction of w2. So just by looking at the picture, what we can say, we can see how I can express u as w1 plus w2. So that's pretty straightforward. The question is, though, could I find w1 and w2 if I am only given u and v? So if I have the vector that I want to decompose, right, and I have the direction in which I want the one vector to be parallel and the other one to be orthogonal, just knowing u and v, how can I find w1 and w2? Well, let's see. So we have a right triangle there, so that's helpful. So I'm going to define theta to be the angle between u and v, right? Those are the two original vectors that we are given. And let's just do a little right angle trig. So let's go ahead and label just the lengths. So the hypotenuse there, which is defined by u, its magnitude or length would be just the magnitude of u. So that's this, right? And then similarly, the red vector here, so we're going to see about finding w1 first. So that distance is just the magnitude of w1, right? That's that length. So since it's a right triangle, let's think about, and here's my theta, let's think about a trig ratio that would give me the relationship between theta, the magnitude of u, and the magnitude of w1. Well, that looks like the cosine, right? So I could say that the cosine of theta, remember that's adjacent over hypotenuse. So the adjacent here is the magnitude of w1 divided by the hypotenuse, which is the magnitude of u, right? And let's go ahead and let's say I multiply both sides by u. So this implies that the magnitude of w1 is the magnitude of u times the cosine of theta, right? Now, suppose I multiply both sides by the magnitude of v. I can do that, right? The magnitude of v is going to be some positive number since v is a non-zero vector. So if I multiply both sides by the magnitude of v, I have this. So the magnitude of w1 is equal to the magnitude of u. Oh, wait, let me get this off. I forgot to actually write it. I said it, but I didn't do it. So let's do times the magnitude of v on this side, and then also multiply this by the magnitude of v. So I'll have the magnitude of u times the magnitude of v times the cosine of the angle between them. Now, why did I do this? Because now I know what this represents. This represents the dot product of u and v. So I could say this. So the magnitude of w1 times the magnitude of v is equal to the dot product of u and v. And then kind of going back, going almost in a circular way, but not a real circle, because we've actually picked up some important information on the way. I guess it could be circular. We still just it's like the dark side of the circle. But if we divide both sides by the magnitude of v, we've figured out now a formula for the length of this special vector in red. So the length of the vector in red is given by the dot product of u and v divided by the magnitude of v, right? So this is the length of the red vector, right? Well, that's great, but what if we wanted to find the components of this? So we don't want to find just the length. I want to know what the components of the vector would be going from this point and stopping right here, right there. Well, what I could do, since I know the length of the vector, if I could find, and I know the direction in which it points, all I would have to do is to find a unit vector in the direction of which v is pointing. And then if I multiplied that unit vector by its length, then I would get the components, right, of w1, right? So if you remember that process of normalizing a vector, so you find a unit vector, and then if you want to find a new vector of a desired length, just multiply that unit vector by that desired length. I have the desired length. I know how to find the unit vector because I have v. I can normalize it, so then I can find the components of w1. So this is what I will say. Since the unit vector in the direction of v is this, we know how to normalize it, so it's 1 over the magnitude of v times v, right? So this is the vector. Notice they're pointing in the same direction, right? Same direction. This is the vector of length 1. Now w1 is going to be the vector of length this, u dot v, over the magnitude of v times this unit vector. So since the unit vector in the direction of v is given by this, the component form of w1, right, is, so here is the nice formula for w1, and I'm going to take its magnitude, which is this, because if you look carefully, notice that this is a scalar, because the dot product is a number, the magnitude is a number, and we're taking the ratio of these two numbers. So this is the scalar, and we're multiplying it by the unit vector in that desired direction. So we end up getting u dot v over the magnitude of v. So I'll put that in parentheses. That's my scalar, and then times the unit vector, which is 1 over the magnitude of v times v. And that's how we get it to be the vector. Now, the 1 over the magnitude is also a constant. And as I said, the u dot v over the magnitude of v, that's also a constant. So what I can do is I can use the associative property and group the constants together and multiply them, right? But before I do that, actually, no, let me go ahead and do that, and then I can give you some new notation and some new terminology for what we're finding here. So multiplying the numerators here, I would have u dot v. Multiplying the denominators here, I have the magnitude of v times itself. So that's the magnitude of v squared, and then this now times v, right? And this special red vector, right? Let me go back up again so you can see it. That special red vector, it is called the orthogonal projection of u onto v. And essentially what it is, it's almost like, so for instance, let me go back up a little bit more. If there was, let's say, a light source directly above u shining down here, and then u casts a shadow on the vector v, then that shadow, the tip of that shadow would be right here, right? And so and another way of looking at it too, the terminal point of w1 is the closest point along the vector v, right? The closest point to the terminal point of u, right? Any other point along the vector v would be further away from this terminal point of u. So it has some really important uses. But let's go ahead and write that down. So w1 is called the projection of u onto v. Now, we don't want to have to write this all the time, so we come up with a notation. This is how it's denoted. In fact, so I'll restate it now. So we abbreviate the word projection to PROJ. We put the vector that is being projected, so we put the u right there, and then the vector that it's being projected onto is placed right there. So this is read the projection of u onto v, and this is the notation that we will use going forward to represent the w1. I just used w1 to say, okay, here's just kind of a generic label, but now that we know we have this very specific formula for it, which I will restate right here, right? This is the formula that we will use, and it gives us the projection of u onto v. Right, so Now you might recognize this formula. I wouldn't be surprised if some of you have used this formula before. And let me go ahead and just kind of box this off. So this is an important formula. So it's a formula that can be used to find this projection quite easily. Now, what about W2? Well, W2 is really, really easy to find because of that formula, that equation that I wrote down. So since U, which we know, right, we're going to be given U and V, and we're going to be finding the projection and this other one that I'm about to define now, which is the W2. Since U is equal to W1 plus W2, then just do some basic vector algebra and solve for W2, right? Because I know what W1 is. It's this. This is what we just found. So this implies that W2 is equal to U minus W1. Just subtract this vector from both sides, right? And again, we know how to do these vector operations. So that means W2 is simply the original vector U minus the projection. So it looks like this, right? And we don't really have another, the PROJ notation is nice for the projection. Some books have a special notation for this other component, and I'll tell you what it's called. This is the orthogonal component of the projection of U onto V, right? So this is this is the formula for it, and this is called the orthogonal projection. Actually, no, this is the orthogonal component of the projection. Yeah, the projection is what we just defined there, that this orthogonal one, and this is called the orthogonal component of the projection of U onto V. Right, so again, let me kind of box off the key parts here. So it's this, so these two, right? So again, let's just kind of summarize with a couple pictures, and then we'll do an example. So if I have U, and again, just for convenient, well, actually, let me draw it like this. So let's say this is U, and then this is V. Then again, the first thing I would do is just to try to create a right triangle, and then maybe I'll do a. So I'll try to write. Yeah. So you create the right triangle there, and then this vector is the U minus the projection vector. So the projection of U onto V. And then the projection vector itself is this vector right there, right? So this is the projection of U onto V. So we find the projection first using this formula, and then use our vector algebra, subtract it from U, and then that will give me the vector in blue. Now, the vectors don't have to be oriented like this. We talked about all the different possibilities for the angle between two vectors. So this is kind of what the picture looks like if the two vectors form an acute angle. But what if the vector forms an obtuse angle? So suppose U is like pointing all the way over there. What does it look like? Well, let's see. Let's see if we could figure it out. So let's say this is U, but let's say V is like over here. So let's say this is V. What would the picture look like? Well, this is where we go back to the idea of closeness. So if I did this and extended V in the opposite direction. So essentially did a vector that's parallel to v, but in the opposite direction. What we're looking for now is the point along essentially this line, right, that is closest to the terminal point of u. This is the terminal point of u, the point along my extension of v, right, that is closest to this point. Again, it's going to form that right triangle. So let's do the right triangle first. So it's, you know, that's horrible. I'm not even going to try to sell that as a right triangle. Let's see if we can do a better job. So the right triangle is more, there we go, much better. So this vector here is the orthogonal component. So that's my u minus the projection of u onto v. And then my projection is actually this vector now. So it actually has to go in the opposite direction. So in order to find, because the angle between the vectors is obtuse, bigger than 90 degrees, you actually have to go in the direction that is opposite to v in order to find that closest point to the terminal point of u. And again, this is the projection of u onto v, right? The nice thing, though, about the algebra that comes into, and notice since the formula uses the dot product, the dot product will handle both cases perfectly, whether the angle is acute or whether the angle is obtuse. So you don't have to worry. You don't have to know how the vectors are oriented, right? The algebra of the dot product takes care of the geometry of the vectors. Really, really cool. All right. So let's look at an example of this. All right. So let's look at an example. And so let's do a 2D example, just kind of mix it up. Some of our examples will be 2D, some of our examples will be 3D, not much difference in the calculation. So let u be the vector 1, 2, and v be the vector 3, -5, right? I am not even going to sketch these. Right. Let's do two things, and I think this example will be a good example, because often students make the mistake that the projection of u onto v is going to be the same as the projection of v onto u. In general, that's not true. So let's actually compute these things. So let's find the projection of u onto v. So let's find that first, and then we will find the orthogonal component of the projection of u onto v and so forth. All right. So to find the projection I'll simply write down the formula and then we'll just fill in what we need. So the projection of u onto v, that's the dot product of u and v over, in fact, what I will do is I'll write down the form right before I simplified it, because there's something else I want to say about this. And then times 1 over the magnitude of v times v, right? So remember, that's what we did. We said that this is the length of the projection, right? And then this gives us the components of the projection. This part right here, since it's a scalar, it is often represented, it's often not represented, it's often described as being the scalar component of u in the direction of v. So this is often described as the scalar, since it's a scalar, component of u onto v, right? So of u onto v. And that's just another way of saying that it's the length of the projection vector, right? So just wanted to mention that. So let's go ahead and fill things in. So u dot v. So we're going to multiply the corresponding components of u and v. So 1 times 3 plus 2 times -5. So that's the dot product. And that will be in the numerator. In the denominator, notice that it's the magnitude of v squared, right? And remember, we previously showed that the magnitude of v squared is the same as the dot product of v with itself. So like if you take the so for instance, if you take the magnitude of v, and I won't simplify this too much, this will be 3 squared plus -5 squared. And then if you multiply it by itself, the square roots go away, right? And then I'll simplify this below, and then we need to multiply this by the vector v. So this is the vector 3, -5. All right, so how does the numerator simplify? Well, we have 3 plus -10, so that's -7. And because the dot product, which is right here, is negative, I know that the angle between the two vectors is obtuse. So it's actually the second illustration that we looked at previously. Just by finding that the dot product is negative, I know that the angle between the two vectors has to be obtuse. The square root goes away, so then I'll have 9 plus 25, and then I have 3 minus -5 as my components. So I have -7 over 34 times the vector 3, -5, and then I can distribute the -3 over, -7 over 34 and get the vector -21 over 34, comma 35 over 34. So this is the projection, this is the vector, right? This is the orthogonal projection of u onto v, right? Let's do part B. It says find the orthogonal component. So the orthogonal component of u onto v. So that's essentially the W2 vector. So that's where we take our original vector u. So this will be, it's going to be u minus the projection of u onto v. Well, what is u? U is the vector 1, 2. So we're going to do our vector arithmetic and get this other vector. So 1, 2 minus what we just found here, which is the -21 over 34, and then 35 over 34. So let's go ahead and get a common denominator of 34. So the first vector here would be 34 over 34, comma 68 over 34, and then minus -21 over 34, and then 35 over 34. Take the difference, so 34 minus -21, so that is 55 over 34, and then 68 minus 35, so what's that? That would be 33, so 33 over 34. So that is the vector that is orthogonal, the orthogonal component of the projection of u onto v, right? And then the last thing we'll do, let's do part C. Let's find the projection of v onto u, just to illustrate that it's not necessarily going to be the same. It could be, but it doesn't have to be. So the projection of v onto u, so the projection of v onto u, well, let's write that down. So it's going to be v dot u, but now in the denominator here, I will have the magnitude of u squared, and that's the big difference. And then this will be times u, right? The dot product is the same. What did we get for the dot product? We got a -7 for the dot product, so that's the same. Because remember, the dot product is commutative. It doesn't matter if you do v dot u or u dot v. So this is still -7. But the magnitude of u squared is going to be root 1 squared plus 2 squared squared, right? Remember, u is the vector. In fact, u is right here. It's the vector 1, 2. Find its magnitude, square it, and then finally multiply the vector 1, 2 by this scalar, and I will get this projection, right? So we end up having, what do we have in the denominator now? We have a 5, right? So we have 5, root 5 squared is just 5. So we have -7/5, and then 1 comma 2. And then I have -7/5, and then -14/5. So this is the projection of v onto u. Definitely not the same as this vector. All right. So there's a projection, and in more like physical science classes or engineering classes, you probably end up using the projection for a lot more things than just computing these vectors. There are some applications of this that we will look at in the future, but for now, hopefully this video has shed some light on what this idea of an orthogonal projection is and how we can use the dot product to find it. See you in the next video.